Okay, so now let's look at first query language, which is the building block, is the relational algebra. This is oftentimes the database, the interface they provide is SQL, but internally they do convert it to relational algebra because it's much easier to deal with the relational algebra as building a query plan and also doing optimization, reordering, and all the interesting query evaluation that gets done under the hood. So query language, again, is a way of and retrieve the data. So kind of how do I extract a set of data, and what I extracted, can I further massage it, aggregate it? With the relational algebra is a little bit more procedural in the way that things gets expressed. But again, it does create the basis and the foundation for query optimization and for expressing database. And the query language is not exactly programming languages. It's different from your Java or C++. And one thing is they're not Turing complete. Not everything can be done. For example, they don't support recursion. That's an important thing that is missing. And it's not really also intended for complex calculation. Like you don't want to build your financial forecasting model in a SQL language and relational algebra, nor that you want to build your deep learning model in relational algebra or in SQL. It's just not intended for that purpose. But they're easy to use, and it's really effective for when you want to process and evaluate a large set of data. And the query language could be the first step of getting a large amount of data, perhaps to pre-computation, massage the data, aggregate it. And so there are two different sort of mathematical model. One is the relational algebra, which we will talk today. It's more operational, and it's excellent for expressing query plans. And so kind of given a query, given even a SQL query, then you look at the sort of the parse tree of these relational algebra that have all the operator within that query plan, which often is a form of a tree. So it's very intuitive in that sense. And once we kind of look at the example, you see what I mean. And then another one is relational calculus, which is less on procedurally kind of defining the steps in order to get your answer, is to really talk about what is it that needed. So more declarative in comparison. So a query is applied to our instances, to our tables. And the very powerful thing is that when you apply a relational algebra query on a relational instance, as we mentioned, the outcome of that or the result of that is also a relational instance. So that's really powerful. That's one of the most important. So they call it, it's closed under composition. That means the input is relation and the output is also relation. So an example, kind of the next set of queries that we're going to work with is we have the sailor and the reserve. So sailor is the name of the sailor, the rating of the sailor, and the age of the sailor. And then we also have a reserve table that captures the SID, which is a foreign key, the SID of the sailor, the BID of the boat itself is also a foreign key, which just points to a boat table. The boat table has the boat ID and the color of the boat, and the day that it was reserved. And these three combinations are key. So usually when there's an underline under an attribute, it represents this is a key. So the key of this sailor table is SID. The key of the R1 is the combination of SID, BID, and day. So that means so let me kind of ask you the question to just make sure. So what's the difference between saying that the primary key is the combination of SID and BID versus saying that the primary key is all three? What would be the difference?
Would that mean that for any given 2, there would be a third that is unique every time?
Hmm? So maybe work our way this way. If we say the SID is unique, what would that mean? If we just say this, the key of this relation is SID. Can this Sailor 22, how many boats can Dustin book if the SID is the key?
I mean, the sailor would be able to have infinite boats. He can have any boat ID.
How many? So
I
how
mean,
many times, if SID was the key, if SID was the key, how many records could have SID 22 in it?
Just one?
So if we can only have one, how many boats SID Dustin can book?
Just one.
Exactly. Uh, so if the SID was the key, then we would limit each sailor to reserving at most one boat. So now what would happen if the key is SID and bit ID?
No two sailors can have the same boat?
Think about it as a one sailor at a time. That might be easier to think about it. What would happen if, let's go back to the Dustin example. If so the Dustin number 22, if SID and bit ID were both, then that means Dustin can book the boat 101, but can it book the same boat twice or no? Or
No.
can it book? So now if these are the combinations is the key, so then that means Dustin can book each boat at most once. If this was the key, then Dustin could book at most one boat. But when I add this to the key, that means now Dustin can reserve every single boat, but each boat it can reserve at once. And now by having the day in there, it now says Dustin can book each boat once a day. So that's kind of how to sort of reason about it. Okay, so now relational algebra. And this is, I think, the most, and I really want to emphasize this, and I want you to kind of, all of you, to take a step back and think about this slide. 50 years of adoption, 50 years of development, 50 years of success in a relational database is founded by simple 5 operation: selection, projection, cross product, set difference, and union. Everything that we do in databases are done by these 5 simple operations, and that's powerful. Is just to think about, you get that set right and look at the impact. For 50 years, those simple 5 operations were sufficient to capture maybe 80% of all the use cases out there. 5, and that's the elegancy, the simplicity of the model. If that 5 simple operation, it's so powerful in practice. So that's really remarkable, is to when we are thinking creatively, it's not necessarily something that is necessarily has to be more complicated. The elegance and simplicity are are really important. The model, the relational model, is simple, just rows and columns. The operations defined on it are just as simple: 5 operations, 5 main operations, rows and columns, and 5 operations. Those seven elements, rows and columns, and these 5 operations has been the force behind almost every data management or almost every software developed in the last 50 years. Universally, you need a database. It's almost everything we do, we need a database. You need to manage the data. And these 7 simple constructs were sufficient to handle that for 50 years. I just find that just really remarkable. And based on these 5, we can define more other ones like joins and division and renaming. And the division one is an interesting one, which we're going to do together. And again, importance of these relational algebra, that it's closed under composition, meaning that if you operate, so you an input, if an input to each of these operations is a relation, the output is also a relation. And since the output is a relation, that can be fed to another operation and yet to another. So you can compose the input of one to another, so that you can make more and more complex operation using these 5 different ones. What are these 5 ones? Selection, select a subset of rows. You already kind of did that for your database. Projection is essentially identify which columns do you want. So the first one, you identify which rows you want. The second one, you identify which columns you want. So if you have 5 columns and you're just interested in the name and age, you use projection. Cross product, it's basically constructing all combinations given 2 relation. Consider all pairwise combination. Simple. Set difference, just essentially minus operation, that set difference. I have some, so I have 2 sets. I have 1 set here. I have another set. I subtract 1 from the other. So you have 1, 2, 3 in set 1 minus the set 1, 2. The result is 3. So just like a minus operation. Union. And union is just, I have 2 elements in first set. I have 3 elements in the second set. They're all unique. The union of that would be 5 elements. If I have 2 elements in the first set, 3 elements in the second set, and the first set was the subset of the second one, the union of the 2 will just be the superset. So that 3 elements. Again, relational algebra by definition or by construction are set. So all duplicates are automatically removed. Any question on that? That's relational algebra. Just one slide. Just very simple. And then we're going to see, even by the end of the lecture, we're going to see how powerful this can be. So projection, again, delete attributes that are not in the projected list. So I have the schema, name, and rating, name of the sailor, the rating of the sailor, and the projection of that. So if you remember, the sailor had more attributes. So sailor had more attributes. So now if I were to project S name and rating, out of the 4 or 5 attributes that the sailor relation had, I only select the S names and the rating. So the result of running the projection on the sailor is to drop the other attributes and just keep the S name and the rating. And if I were to project age from the sailor, I only get the age column. Of course, if there are multiple sailors with the same age, I would get multiple record for that age. But since relational algebra is set, all the duplicates gets removed. So only unique rows remain. Any question? Okay, pretty straightforward. Selection is you provide a condition and you select all the rows that satisfy that condition. No duplicate because it's set. So selection, rating greater than 8. So all the rows who have rating greater than 8 are selected. So the the row had the rating 8 and 5 don't satisfy the condition, so they don't appear in the final result. Straightforward. And the schema are also identical, because so the schema of the input and output is identical, because with the projection we can essentially modify the schema. So the projection is the ability for us to modify it, but the selection is just same input, same output. Of course, we can compose it. So we had the rating at 9, so we first select those rows that have a rating greater than 8. Then we project the name and rating, meaning that we only going to extract the name and the rating column. So that would be the resulting relation. Okay. And also this was an example of composition. The result of the output of this relational algebra expression became the input of the second expression. So that's the composition. This, so the result of this, so this was the input. This is the result of the first expression, also a relation. So now this is fed to yet another relational algebra operation. The output of that, again, a relation. So again, this can be fed into yet another operation. And so this is the way we kind of incrementally build upon kind of be able to express more and more operation. And we're not defining how to filter out rows. So it's not procedural descriptive in that sense. So it is more so it is operational. So we kind of says, well, just give us everything that is greater than 8. And then once you get greater than 8, it does have some procedural aspect to it that we say, okay, now then project out certain columns from it. So examples of the set difference and union. So again, if I get two relation S1 and S2, the union of that S1 union S2, again, would be just a combination or just the both of them together with a duplicate removed. For example, Dustin appears here, Luber appears here, but also Luber appears in both tables. But in here, we only have one row for Luber. And Rusty again appears in both, but here we only have one row for Rusty. And then the group P and UP, Yuppie is, well, they don't appear, they only appear once, and of course they appear in the final set as well. We also have, we can define the intersection, and then the intersection is just what is common between them, the overlap. And then the set difference is S1 minus S2. Dustin doesn't appear in S2, so Dustin is a qualified. Luber appears, is not qualified. Rusty appears, not qualified. So that's the set difference. And cross product is just pairwise combination. So basically, again, I have the two relation on the top, S1 and S2, S1 and R1. They don't have to have the same. For set differences, the schema had to be the same. For cross product, the schema doesn't have to be the same. And the result of the schema is that every row in the first one gets paired with every row in the second table. So Dustin gets paired up with both of these rows in R2. Luber gets paired with everything. Rusty, it also gets paired with everything. And so Dustin gets paired with 22, with both 22 and 58. Luber again gets paired with everything. Rusty also gets paired with everything. If you have duplicate column ID, that becomes some implementation detail a little bit. you could carry over the table name to resolve the conflicts, or we could have a renaming operation that says, well, the first one is called SID-ID1, or this, and the fifth column called SID-ID2 as a result of the cross product of S1 and R1. Is this meaningful? We're just simply looking at all combinations. But this becomes the basis of joining tables. In this form, is we may say, okay, what's the point of just randomly pairwise looking at all combination? And you're right, this is not being really meaningful, but that becomes the basis to do join operation. And that's really, this cross product is probably the most important product and the most expensive operation in relational algebra, and it's just the basis for everything. This is the basis for anything that goes beyond a single table. As long as the moment you want to go cross tables, cross product is the fundamental operation. So now we can define joins based on the cross product. Join has a condition, and for example, we can say the condition is that SID-ID, so this is a join, this is a theta join, saying that this S1 SID is smaller than R1 SID. And if this condition is met, then the row becomes qualified. So the join is essentially doing the cross product, randomly considering all possible combination, and then filtering out any row that doesn't satisfy this condition. So let's see what we have. We have Dustin 22, row 58. Luber 31, and then 58, both, and then the SID 58. And we see that S1 S1 22 is less than 58. S1 31 is less than 58. But if you go back to the cross product that we had, so here S1 is not smaller than 22. That's why this wasn't selected. S1 is smaller than 58. This was selected. Luber 31, 32, this doesn't satisfy it. That's why this row wasn't selected. Luber 31 and 58, this does satisfy it, and that's why it was selected. These two, 58, 22, neither of these two rows satisfy that condition, which is why it wasn't selected. But that simple cross product becomes the basis of doing these meaningful and practical application, sort of logic-driven joins. So a conditional join is that essentially we do blindly a cross product, then apply the filtering condition. Of course, this is nobody in the database, you don't actually go ahead and implement the join that way, but in terms of formalism, that cross product is sufficient operation to support, to be able to be as a building block, at least in terms of formalism, for any kind of complex type of joins. So, and the result schema is the same as of that cross product, but fewer tuples than the cross product, because essentially we start with the cross product and then we eliminate some rows. Of course, there's more efficient way of implementing this. Doesn't mean that that's the way that it needs to be implemented. And this is also, again, as mentioned, is called the theta joins. There's also equijoin, which is kind of, it's the equality, is a special case that kind of said the equijoin and SID. So select all tuples that the SID in the R is equal SID in S. And in this case, these were the two rows, and we only put SID once because they are equal. So that's, again, that's implemented based on over the cross product. It's a combination of cross product and projection. So, and again, the outcome is, the schema is identical, except that this SID only repeated once. And again, you can just take a cross product, do the filtering condition saying that the SID R SID is equal SSID, and then projecting the second SID out, meaning only including the first SID. So again, this can easily be implemented and translated into those basic 5 operations that we had. And there's also, so we have the echo join that is on one particular column or on that condition. And we have a natural join, which is kind of doing echo join on all columns. Of course, if you do echo join on this relation, that won't work. Point is a good stopping point right now. And so we're more happy to answer any question you have. And so have a wonderful day. And thank you so much.